Hello, everyone. My name is Yunju, and I'm from Zhejiang University. Now I'm a research intern at Ant Group, and I will give a talk about GraphRag survey. My talk is divided into the following 5 parts. The first part is about research background, and the second is overview of GraphRag, and third is about related technologies of GraphRag, then applications and evaluation. And the last part is about summary and prospects. As for the first part, research background, LLMs have demonstrated great capabilities in understanding and generating text, greatly advancing the field of NLP, but they still suffer from out-of-data knowledge hallucination generating unreliable text. To supplement LLMs with external high quality and updated knowledge, RAG has emerged. It improves the quality and relevance of generated content by integrating a retrieve component during the text generation process. The essence lies in the ability to dynamically query larger-scale text databases, injecting relevant factual knowledge into the response generated by LLMs. However, in practical scenarios, text content does not exist in isolation, but is interconnected, and RAG often retrieves a large number of text fragments, which may lead to excessively long input text for LLMs. Due to the factor that RAG can only retrieve a portion of documents based on semantic similarity, it struggles to preserve global information, thus facing shortcomings when addressing global issues concerning the entire corpus. GraphRag emerges as an innovative solution to address these challenges. It retrieves graph elements containing structured knowledge from a pre-built graph database to answer complex user queries. Therefore, it fully considers the structured relationships between texts, thereby retrieving relational data more accurate. Furthermore, because graph data is often a further abstraction and summary of text data with a lower degree of information redundancy, by retrieving subgraphs or graph communities, it is possible to capture a broad context and interconnectivity within the graph structure, thereby obtaining more comprehensive information. This is the compression of direct LLM, RAG, and GraphRag. Given a user query, direct answering by LLMs may suffer from shallow response or lack of specificity. RAG addresses this by retrieving relevant textual information, somehow alleviating the issue. However, due to the text length and the flexible natural language expressions of entity relationships, RAG struggles to emphasize inference relationships, which is the core of the question. Well, GraphRag methods use explicit entity and relation presentations in graph data, enabling precise answers by retrieving relevant structured information. Next, I will give the overview of GraphRag. The core objective of GraphRag is to retrieve the most relevant structured knowledge from the graph database in relation to user queries, thereby enhancing the relevance and accuracy of the response. A graph retrieval and text generator can be used to model target distribution and decompose it using the total probability formula. GraphRag can be divided into these 3 stages: graph-based indexing, which will select or construct a graph database corresponding to the downstream task and establish an indexing on it. Graph-guided retrieval will extract the most relevant graph elements from the graph database based on user queries expressed in natural language. And graph-enhanced generation will deeply integrate the query with the retrieved graph elements to generate a response to the user query. There are subcategories of each component. We will give a detailed introduction of these techniques in the later part. This figure shows the overview of GraphRag framework for question answering task. In OSFA, we divide GraphRag into 3 stages: G-indexing, G-retrieval, and G-generation. We classify the retrieval source into open source knowledge graphs and self-constructed graph data. Different enhancing techniques like query enhancement and knowledge enhancement will be adopted to boost the relevance of the results. Unlike RAG, which use retrieved text directly for generation, GraphRag requires converting the retrieved graph information into patterns acceptable to generators to enhance the task performance. Next, I will introduce the GraphRag related technologies. First, I will introduce the technologies of graph-based indexing, which include 2 main parts: graph data and indexing. OSFA classify graph data into open and self-constructed knowledge graphs. Furthermore, open knowledge graphs can be subdivided into general knowledge graph and domain knowledge graph. And self-constructed knowledge graph mainly use raw data to construct a private graph database. Graph-based indexing plays a crucial role in enhancing the efficiency and the speed of query operations on graph databases. Directly influence subsequent retrieval methods and the granularity. Common graph-based indexing methods include graph indexing, text indexing, vector indexing, and hybrid indexing. In GraphRag, the retrieval process is crucial for ensuring the quality and relevance of generated outputs by extracting pertinent and high-quality graph data from external graph databases. We classify this core part into retrieval paradigm, retrieval granularity, query enhancement, and knowledge enhancement. As for graph retrieval, non-parameter retrieval is based on precise rules and algorithms. These methods achieve higher retrieval efficiency, but retrieved results are not sufficiently refined. And language model-based retrieval is based on measuring the similarity between text and graph data. It is able to fully leverage the rich textual information, but incurs higher time complexity. And GN-based retrieval uses GN to model graphs and identify keynodes and edges. It can capture a broad range of structural information, but requires supervised signals for training. As for retrieval paradigm, we classify it into 3 categories: single retrieval, iterative retrieval, and multi-stage retrieval. Single retrieval means conducting a single retrieval or multiple independent retrievals. It offers lower time complexity, but often results in less precise retrievals. Iterative retrieval performs multiple retrievals, with each one depending on the results of the previous round. This method offers better performance by progressively refining results, but is generally inefficient due to higher computational costs. To effectively balance retrieval accuracy and efficiency, a multi-stage retrieval strategy is employed, leveraging different retrieval methods or retrievals at each stage. The retrieval granularity can be classified into 4 types: node, triplet, parse, and subgraph. Each type has its own set of advantages and disadvantages. The retrieval enhancement aims to ensure high retrieval quality, which consists of query enhancement and knowledge enhancement. The query enhancement can be further divided into query expansion and decomposition. Query expansion means supplementing the query with additional information to make it more specific. Query decomposition will break down query into smaller, simpler query subqueries. Knowledge enhancement can be divided into two main types: knowledge merging and knowledge branching. Knowledge merging combines and summarizes information from different sources to create more complete understanding. Knowledge branching removes irrelevant or unnecessary information. And the third part is graph-enhanced generation. Generators can be classified into GNs, LMs, and hybrid models. And the graph data can be transformed into graph languages or graph embeddings, enabling generators to process and utilize the information more effectively. Generation enhancements like pre-generation, mid-generation, and post-generation enhancements are employed to improve the quality of outputs. Pre-generation enhancement aims to enhance the input to the generator, like graph rewinding and graph augmentation. Mid-generation enhancement modifies the generation strategy using intermediate outcomes or contextual cues from the query, including prompt engineering and Bing search. Post-generation enhancement refines the generated content by merging answers to different sub-questions and integrating response from multiple generators. As for the model training, retrieval training is divided into two approaches: zero-shot methods and training-based methods. Zero-shot methods do not require additional training like non-parametric retrievals and prompt learning. Training-based methods involve further training on target data to enhance performance. As for generator training, also can be classified into zero-shot and training-based methods. Joint training integrates retrievers and generators either by refining them into a single model and training them simultaneously, or by training them separately and then fine-tuning both together, thereby enhancing downstream tasks. And the first part of applications and evaluations, the downstream applications contain question answering, information extraction, and other tasks across different domains. And the last part is summary and future prospects. RAG introduce external information into LMs to refine the output, but there are issues such as inability to capture relationships between texts. GraphRag further enhance the quality of answers by retrieving structured knowledge relevant to the question, capturing the global level information. For better analysis of GraphRag, we divide them into three main stages: graph-based indexing, graph-guided retrieval, and graph-enhanced generation. And we can find GraphRag is promising, which has a wide range of applications across different domains. In the future, there are many directions worth exploring, like dynamic GraphRag, multimodal information integration, building benchmark for GraphRag, and more. There are external links of our GraphRag paper. For more detailed information beyond this talk, please refer to our paper. Thank you, that's all.